Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Matt Martin, Managing Director of Oxford Instruments Nanoscience. Matt describes his company's focus on dilution refrigerators for quantum computing, the differentiation between different refrigerators, modular designs, and scalability considerations. We also cover service, maintenance aspects, recent developments, and much more. We hope you enjoyed this episode. Hello, Matt, and thank you for joining me today.
Thank you, Yuval.
So who are you and what do you do?
So my role today is actually the Managing Director of Oxford Instruments Nanoscience, which I've been doing for 6 months. But actually, prior to that, I spent 4.5 years here as the Director of Engineering, where I've been looking at our product portfolio and basically been rebuilding our roadmap and our collaborations, and that's been really exciting.
And what does Oxford Instruments do?
So Oxford Instruments Nanoscience, what's its reputation? So Oxford Instruments as a business was the first spin out of Oxford University, focused on superconducting magnets and cold dilution units. This is 1959 time, so we've just over 60 years. So effectively, in terms of the quantum space, we are probably the most historic company doing dilution refrigerators and very large magnets. And our history has entirely been providing research equipment into the materials measurement and materials characterization markets.
I like that. So quantum will be an overnight revolution, 60 years in the making.
Mm-hmm. Pretty much. Well, as any company that's been stuck around for a while finds out that if you don't keep an eye on the market, it will move underneath you. And I guess it's what we all want to be, is relevant to today.
So educate me if you can. Obviously, dilution refrigerators are used with superconducting qubits. Now, I work for a company that makes neutral atoms. We operate at room temperature. But let's say I was in the market for a dilution refrigerator. What sets one vendor from the other? What are the important characteristics of a dilution refrigerator?
That's a very, very broad question, and very much depends on what you really want. So if there's a lot of rumor in the market, and ultimately, if I really distill it down, in superconducting qubits, what does a DR do? And the answer is it provides a cold environment. So provided it provides that cold environment reliably, repeatably, and allows it to stay cold for years at a time, it's probably meeting the requirement. Now, obviously, then there's a lot of talk in the marketplace that says, but if your dilution unit, the engine in your fridge is slightly different, does that make it better or worse? Well, I'm sure that all the purists that are involved in the science of making dilution units will say, well, of course it makes it better or worse. But if I take the analogy of your classic automotive vehicle, whether it's an electric powertrain, whether it's a diesel powertrain, the things you care about are the cost to run it, whether it's environmentally efficient, and whether it actually gets you to the shops and back as you plan. So I think there's always that thing where people try and create, should we say, sectioning between companies about what their products do. In reality, for the superconducting community, if it gets cold, if it stays cold, it can hold enough wires and it can manage the heat load, it's probably competent. And then the question then is, well, are you an Audi driver or a BMW driver or a Mercedes driver? Everybody will has their preference, but at the end of the day, it's still a good vehicle.
What sets your company apart?
So we have made the coldest continuously operating dilution refrigerators. We have systems that can comfortably go down to 4 millikelvin and stay there. We've got some of the lowest vibration systems in the marketplace for the research space. And for us, we've taken a very close look at the market when we did our Proteox range, probably 3 or 4 years ago, recognizing that quantum was a thing, and said, well, how do we get a lot of wires into a very, very small space? And how do we make sure that whenever you've got to make a lot of connections, there's always a reliability question. And if I have to make 1,000 wires and connect them all inside a fridge, how do I know that they will all be good? And so we said, well, let's do our wiring off system using a thing we call a secondary insert, qualify it, and make sure I can move it between a small fridge, a medium fridge, and a very large quantum scaling fridge like the Proteus QX, it's always the same. Yeah, it can always go in the same thing. And if I've qualified the experiment small, then I can, with confidence, take it all the way through to large. So we really looked at modularity, and we tried to understand the quantum scaling market when we designed the product. And that's the feedback we're getting back from the customers, going, wow, somebody's actually done modular properly. And that's actually really positive to get that sort of feedback from people. Because you know what it's like, you talk to customers and they go, we want a thing. But of course, sometimes what they say they want isn't what they really need. And so there's always a bit of interpretation about the want and the need thing. And we're really pleased to see the feedback we're getting from that approach.
How well does it scale? If I went from 100 qubits, 100 superconducting qubits to 10,000 in a couple of years, so how well does it scale in terms of, is it a single fridge, is it multiple fridges? How does power consumption scale? Anything you can share with me about scaling would be wonderful.
That's a really good question, and there's probably a few things to pull out. One is about cooling power, one is about the wiring scaling, one is about the total capacity of the fridge. So I'll probably go back to my modular answer to that. So if we take a small fridge, we have a bunch of components that make that fridge work very well for us. There's an OEM like a pulse tube. There is the dilution unit itself. There's the wiring solution. There's the gas gap heat switches, which we use to control the temperature between the top and the bottom of the fridge and cool it down. And in the small version of our fridge, the thing that we call Proteox MX, all of these components exist. When we go to the larger or the mid-scale version, the same things exist, but in a multiple of 2. So we've got the same gas gap heat switches, we've got the same secondary insert, we're using the same pulse tubes, but the form factor is still round. Now, when we went and looked properly at scaling, anybody who's tried to tessellate anything finds out that round things don't tessellate very well. So we asked the very simple question: if I needed to put lots of these things together, what's the best shape that tessellates well and easily? And the answer is, well, people are very used to laying out squares like chessboards. And we said, well, how do we make sure that all the connectivity between all of these common elements go together? And we said, well, we'll just put lots of squares in a line. We'll have access front and back, and then all the connectivity faces will be side and side. And how long can we make the line? And the answer was, well, we could probably make the line as long as anybody wanted. So to go from a few hundred qubits in our single secondary insert to 200, 300, 400 qubits on a 2 secondary inserts to perhaps 1,000 or more qubits on many secondary inserts, of which I can put multiples of in modules of QX. We've built a very, very modular and linear model. So effectively, a QX for us is a block, it's a square. I can put 4 or 6 of these secondary inserts in it, and then I can put as many QXs together as I like to create an environment for 1,000 or 2,000 qubits. So that's the wiring and the modularity question. But the real question then is cooling power and environmental efficiency. Today, there are a number of pulse tube manufacturers in the market space. Yeah, and they'll sell you pulse tubes that will do 2 watts of cooling at 4 Kelvin, or maybe now with the Crimec team, 5 watts of cooling at 4 Kelvin. And we can use multiple pulse tubes in each of our QX modules to scale up that cooling power requirement. And then we can use multiple DUs in each one of those cubes to create the cooling power requirement for the qubits at the mixing chamber. And that's all very easy. But then if you want to start taking 2 or 3 or 4 of these modules together, then obviously you've got to work out how you do the joining, how you manage the radiation, how you manage the vacuum, how you manage the performance loads. And then we get to a fridge where you could easily have 16 or 32 pulse tubes in it because it's 4 units long. And you go, wow, that's a lot of pulse tubes. And then you get to this question of going, well, when is it efficient not to use a pulse tube? When do you go to a different cooling methodology, perhaps like using bulk cooling? And people go, well, what's the cost of bulk cooling? Well, you go and talk to people like Air Liquide, or you go and talk to people like Air Products or anybody else, and they'll give you some very big numbers, millions of pounds for proper bulk cooling plant. And then you go, well, I can buy a lot of pulse tubes for millions of dollars. Yeah, and then there's the question about, well, what's most important? Is it cost or is it cooling power? And I think depending on who we talk to for our customers, that answer is different. So I think what we've done as we've been developing our scaling products, Yuval, is understood properly what people are asking for. Because everybody's actually asking for the same thing, but with different requirements. And it's only by going through those conversations that we've actually gone, are you a multiple pulse tube person or are you a bulk scaling person? And without breaking any of the confidences of the conversations we've had groups of customers that have each answered that question differently. So it's a very long answer, but it's actually quite a complex question. And everyone went, well, going back to my original point, what makes your fridge different? And I said, well, provided it gets cold and stays cold for a long time, then all fridges are sort of the same when it comes to being an environment for a superconducting qubit. What makes it different, perhaps, is the way that you scale and the consistency of the components you use, and the fact that you genuinely have a modular system, which means that the limit is n. And then ultimately it comes down to how much money you've got in your pocket.
If I spoke to some of your customers, and I know some of these relationships are confidential, would they also concur that cooling is not the major hurdle to scaling the number of qubits?
Okay. So cooling is a hurdle. And depending on what they want to do, cooling will matter. And of course, depending on what you want to do, the thing that lots of our customers will talk about is wiring solutions. So we all started with coax. Yeah, and all of the research work was done early on coax wiring. But anybody who's really trying to scale is coming up with their own wiring solutions, whether it's a flexible wiring solution. There's a whole bunch of work going into cryo-CMOS, and when will multiplexing change the game? And then, of course, when you then talk about sticking cryo-CMOS in a fridge and the how you manage the cooling requirements of that, that's a very different story again about where you need to take the heat out in a fridge. So again, when you go from the brute force approach that people are talking about at the moment, to potential the future fridge, which is a scaling fridge that then doesn't use brute force or doesn't use flexible wiring, but might use multiplexing, whether that's optical or RF, there's a whole bunch of new cooling challenges to be resolved. And I guess the question is always, what matters most to you? Because depending on what other programs a customer has got, sometimes they go, give us the biggest space under the mixing chamber because we've got a lot of wiring we need to resolve. Other customers are going, give us the biggest space and the most cooling power at 4 Kelvin because we've got a lot of parametric amplifiers or cryo-CMOS we want to cool. And other people have said, we just need space. Just give us the biggest thing you can possibly give us. How many modules can I have together? Yeah, what's the budget? That's okay. What we need to do is do the experiment because we need to prove that actually we will solve our issue with error correction by just having more and more of it and then proving that a big system will work. Yeah, because that's part of their roadmap. And again, I don't want to break any confidences, but every single one of those questions has been asked differently by any number of customers in the last couple of years. So when we launched Protox QX at APS last year, we launched a concept. We didn't launch a product. Everybody's taken the concept and gone, can I have one that's green? Can I have one that's bigger? Can I have one that's taller? Can I have one that's a specific requirement for our roadmap? And actually, that's been really enjoyable, getting to properly understand what people want and actually provide solutions to it. Purely and simply, I had a bunch of engineers that have been doing fridges for years, and those fridges have been going into research, and they've enjoyed making the lowest vibration, they've enjoyed making good cooling powers, and they've enjoyed creating better automation software. But ultimately, it wasn't a completely different challenge. It was just build me a better X. Whereas going to scaling, it was a very, very different concept that the engineers had to work through and the scientists had to work through. And that was a challenge. And so people have actually really enjoyed those conversations.
I'm curious, are dilution fridges a significantly growing part of your business? Is it just a small thing and you have a lot of other non-quantum things that are really keeping the lights on?
No, that is another great question. So years ago, we started talking about the quantum wave. Yeah, and the reason we coined it is quite simple. The quantum is such an attractive market. There is so much investment going in. Yeah, everybody goes, God, you've got to put all your efforts into quantum because otherwise you'll miss out. And that's true. There is such an opportunity here. But fundamentally, we're doing work to support superconducting qubits and potentially spin. But which modality of qubits will win? Will the NV guys win? Will the photonics guys win? Will the superconducting guys win? The answer is nobody really knows today. We know where the bulk of the investment is going, but just because that's where the money's gone doesn't guarantee that that's the space that will become successful. So I mentioned at the beginning that we're a company that provides environments and measurement capability. So as much as we're focusing on quantum, the core historical measurement part of our business, for customers doing electrical transport measurement, thermal, any number of different variations of those things, is still something that we are completely focusing on. So quantum is only one of the two pillars that are part of what we do. We've got products like our Tesotron or our SpectraMag that are used in research universities throughout the world doing general materials characterization. And that's not a market we're moving away from. If anything, actually, we're trying to reinforce that market for the simple thing that we don't know which quantum modality will win. And you don't back, if you're spread betting, all of your money on one horse. So no, very much we're looking to underpin our historical dominance in magnet technology. We're doing some great collaborations with people like the Mag Lab in Florida and with European projects like Isabel, the MFL, to try and drive that future magnets technology where we're moving from LTS to HTS, as much as we're doing all of this work in trying to scale quantum with other customers, which is probably what makes it such an exciting time for Oxford Instruments at the moment. Yeah, we've got so much to do. We've had to grow the team dramatically in the last couple of years to do it. Yeah, and trying to find people that understand large-scale systems on one hand, as much as we're trying to find more and more research application scientists, PhD physicists on the other to drive our measurement market. We've almost got two camps forming inside the business about the way we need to operate. One is an industrial company, and one is an absolute materials research instrument company. And then that's been great trying to manage that transition.
Quantum is changing very rapidly. So I'm curious, what do you know today that you didn't know, say, 9 months ago?
We know that various companies have got great roadmaps, and being able to work with them and see the directions they're going in and how that's affecting our product has really changed some of our thinking. So we know that the way people are trying to scale is different than we thought it was, which we certainly didn't know 9 months ago. We know that as part of trying to understand what those challenges are, we find out that we can perhaps contribute more to those roadmaps than we thought we could. And I'll give you for instance, people were treating cold as cold. And when you go, well, how do you want to get cold? How do you want to route your wires? How do you want to install a system that's going to weigh many tons? Yeah, and actually will have maybe dozens of racks of ancillary equipment. It became a question that wasn't just about scaling science. It became a question about how we fitted our fridges with customers like OQC to data centers. Yeah, what does the environment look like? Yeah, what are the constraints of the data center? We never knew that 9 months ago, but we do now. When we talked about scaling and how you physically fit a fridge, which is 4 tons, and then you put 2, 3, or 4 of them together and say, well, how do you get that into a building? And how do you manage the vibration? And how do you manage the installation? And what was the service engineer commitment to support that large scale installation look like? We didn't know that 9 months ago. So yeah, we've really learned in both ways about how effectively the superconducting qubit is translating into application requirements. But for us, we are not making the computer. We're the support team. Yeah, we're the pit crew that says we can make your car, your environment work. And the constraints of all of those people looking at how they deploy have taught us loads and loads of different things in the last 9 months. Yeah, some of them really simple, which actually industries like semi could have taught us anyway. Some of them brand new, because actually, when was the first time that anybody put a quantum computer in a data center? And the answer was that all happened in the last 12 months. And now we've done 4 of them.
If there's such a thing as a typical project, how long does it take from here's a purchase order to now you want me to sign off on the delivery?
So if we've done a lot of work in our factory to sort out lead time. So for our standard product, if you bought a standard fridge of us today and you dropped a PO and it fitted our standard configuration, we could ship that to you in under 6 months. If you came to us and said, we've got a real bespoke requirement here, depending on what you're asking for, that could take anywhere between 9 months, a year, or be a 2-year program. We've got a great history of doing perhaps some world-leading equipment, both in DRs or in magnet systems with dilution fridges in them. It's won people Nobel Prizes, but some of those are really quite complicated, bespoke projects. We enjoy one as much as we enjoy the other, but it really depends on your requirement. What we're trying to do is move away from doing lots and lots of these bespoke things at the moment, purely and simply because that's how we've liberated the capacity to focus on the quantum scaling. Yeah, as a business, you can't focus on everything. So we've made some really, really clear decisions on looking after the general measurement market and focusing on quantum and quantum scaling. Yeah, they're the two key pillars that we're really, really working on at the present time.
If I run maintenance for a significant data center, now you deliver a dilution fridge to me, do you need to train me in things that I don't know how to do today? Do you leave a person behind with the fridge to help with the maintenance? How does it work on that perspective?
So to date, with the industrial scaling, we've done a lot of work developing service solutions for people. Some of our customers say, well, how do you train us? And we want to do it. Most of them have gone, well, actually, what we want from you is the environment. So therefore, we're willing to purchase the spares contract, the service contract. We want that 24/7 or 5/8 support. Yet you make our problem go away. That's your part of the solution. So our service team have really enjoyed going, right, how is that different from what we provide today? And actually, from our plasma team are used to doing service models. They do it for customers all of the time. So it's the great advantage from being part of the Oxford group. We just walked over to the plasma guys and went, give us your service contract schedule. How do you deliver 24/7 support to a plasma tool? And they went, we do it like this. And our service team went, that looks like a great playbook. I'll borrow that. And that's exactly what we've done. We borrowed knowledge from across our business and said, we'll do that for a fridge. And that's been great to be able to provide those services.
As we get to the end of our conversation, I wanted to ask you a hypothetical. If you could have dinner with one of the quantum greats, or maybe the refrigerator greats, who would that person be, dead or alive?
So that's a... I don't... How do you define the greats? And I think that's always a question. I'll answer it more personally than that. My background's actually semiconductors. So I spent the first 20 years of my career in companies making plasma etch, plasma CVD. So different physics. So when I first came across to this industry, I went, what do I need to learn about quantum? So I actually went onto YouTube and went, right, who's got some stuff up there? And I actually spent a good period of time watching a lot of Andrea Morello's videos on introducing quantum. So I've never met the gentleman, but I would really love to actually spend dinner with him and say, thank you very much for that entire video series that you did. And actually, can we talk in person? So I don't know where you put him in the pantheon of quantum physicists, but for me personally, I found his videos characterful, entertaining, insightful. So no, I'd love to spend some time. I'd love to have dinner with him.
Wonderful. Matt, thank you so much for joining me today.
No, thank you. A pleasure.